This is a talk that's ostensibly on features and constraints, which is discussed in our textbook, Poole and Mackworth, on the importance of featural representations for states. But really this is going to be more of a story about the application of machine learning. Here is a rotogravure printing press. These are huge printing presses. They're used to print newspapers and magazines and books as well. If you Google rotogravure images, you'll find lots and lots of pictures of brand spanking new printing presses. I've actually been to a large plant of R R Donnelley Sons in Gallatin, Tennessee, and have various colors that's splattered around. But despite all this, these printing presses put out a very good product. There are 8 printing units organized into sets of 4. Each set of 4 is dedicated to one side of the paper, and the paper is stored under the floor. It's, I don't know, at least a ton, maybe several tons, and it's fed up through the floor to the printing units. It goes through 4 of the printing units, each dedicated to the primary colors of yellow, red, and blue. And there's typically a separate printing unit dedicated to black. You could recreate black from 3 primary colors, but turns out it's better quality if you have dedicated units for black. One side of the paper is printed on 4 of the printing units, and then the paper is flipped and the other 4 printing units print the other side. So here's a close-up of one of these printing units. At the very bottom there's a bath of ink. It's called the ink fountain. And just above it, rotating at very high speed, is a chrome-plated copper cylinder. In the diagram, the arrow is pointing at a gravure cylinder. And on that chrome plating, an image is engraved. It's a very complex image. It includes text and pictures and other things. It basically corresponds to whatever you want to print. That's engraved there through a process that we're not talking about right now. And then this impression roll, which is at the top, is pressing a continuous supply of paper against this fast rotating chrome-plated copper cylinder, and the paper's pressed against it, and the image, as the chrome-plated cylinder rotates through the bath of ink, the recesses created by the engraved image pick up the ink and press it onto the paper. Now each of the printing units is dedicated to one color, let's say the yellow. This paper is going through the system so quickly that yellow gets printed, and before it dries it's going through another press for blue or red. And that other press has the same image engraved on it, except at a different depth perhaps. So if you want a lot of yellow in one part of the image and only a little blue, the blue of that image would be shallow, and the yellow part of that image would be deeper. So you can combine amounts of ink in appropriate proportions to create any kind of color that you want to. Again, in this day and age, it seems like it's fairly primitive, but it works pretty well. Now, what can happen on one of these chrome-plated cylinders is that something known as a cylinder band can become engraved through whatever means, not intended, can become engraved on the chrome-plated copper cylinder. As you'll see in a moment, this engraving, this cylinder band, picks up ink, and that ink is transferred onto the paper, and it can degrade the quality of the finished product. If you're falling asleep, I find that an article on relationship fitness always gets people's attention. There you see some lines down there towards the bottom of this article. And those lines are the result of a cylinder band. So the cylinder band was engraved on the copper cylinder. It picked up ink, and so we would somehow have to repair that cylinder, because people paying good money for these printed products are not going to want to have bands running throughout their product. So here's some context at one large printing plant of R R Donnelley Sons. These plants run 24/7, and they have hard deadlines. They've got to get product out for the morning newspaper, the magazine inserts, or books being shipped, whatever. But they're going all the time. In 1989, this plant experienced 538 bands. This was too many. This became intolerable because each band requires 1.5 to 6 hours to remedy. In some cases, you can polish the band out if you catch it early enough. In other cases, you've got to strip off the chrome plating, replate it, re-engrave it with the appropriate image, and then things up again. And that can take a very long time. And it takes the time of crew who are also working the printing press. My collaborator, who was really the lead on this, Bob Evans, decided that machine learning might be a good approach to solving this problem that become very problematic at one plant. But this is an industry-wide problem. Before you can apply a machine learning system of the type we were using, you've got to collect data. And here's where the featural representations for states come in. Variables are used to describe the printing press at different points in time. Each variable or attribute has a domain associated with it of legal values. The variables or attribute can correspond to individual printing units, characteristics of individual printing units, like the ink viscosity at one printing unit, or the ink temperature at that printing unit. They can be printing press-wide characteristics, like the type of paper that's being used, or the rotational speed of all the printing units. They can refer to ambient conditions, like the ambient temperature and the ambient humidity. So lots of different kinds of variables here. There's over 30 listed in this table. We could go in and tweak one of these variables, let's say chrome solution ratio. We could tweak that in some way, and that would change the operating state, the system state of a printing press. Poole and Mackworth talk about the equivalence of featural representations like this and state descriptions that you would think about in state space search. Suffice it to say that states require some sort of formal representation. Variable value pairs, 30 in this case, would be a common way of representing formally system states. So how do we get this data, and what do we do with it? Essentially through manual means rather than automated sensors. Through manual means, snapshots of the operating printing press were taken. You can think of each snapshot as a state description, the state that that printing press was in at that time. And these are just values that were collected at various points along the variables. So literally they took the temperature of the ink, one of the sample printing units, when they were taking one of these snapshots. And importantly, they took snapshots when a printing job, as it's called, banded. When a band formed, since we wanted to avoid bands, it was important to take system snapshots when they occurred. It was equally important, though, to take system snapshots when they didn't occur, because after all, the whole goal here was to learn the conditions under which a band would not occur. And so it was important to get these snapshots in both cases, when a job did band and when it didn't. There's interesting stories about many aspects of this process that I won't talk about here, but you can find in reading if you choose to follow up. So after getting these snapshots, we got about 500 such snapshots, each of 30 features each, about half banded and half not. We used machine learning to learn patterns of variable values, of when banding occurred and when it didn't. From the data, we learned or discovered patterns. And these patterns suggested the conditions under which banding would occur and banding wouldn't occur. And again, the point here was we wanted to learn these patterns so that we could avoid bands in the future. And so these discovered patterns were actually turned to constraints for the operating crews to follow. An example of a complex constraint down here that operating crews were told to follow. And again, I'm oversimplifying the story a bit because you can read about it elsewhere, is if the chrome solution ratio was greater than a certain threshold, and the ink temperature was less than or equal to another threshold, and the ink viscosity was greater than still another threshold, then banding was unlikely. And so operators were told, adhere to these rules, adhere to these specific thresholds, and you will avoid banding. And sure enough, when crews implemented these rules, when they started implementing these in 1990, they started to see a decrease in bands. In 1989, again, there were over 500 bands. In 1990, there were almost 400, but a significant reduction in bands. And this reduction continued until 1994, in which there was a blip. And in fact, the conditions that had been learned through machine learning actually were instrumental in discovering what was really going on, why that blip occurred. It was because of contamination that had been shipped to the plant. So even in this case, the patterns that were learned were important to help solve the problem. And this reduction in band, this large reduction in band, continued up until, so far as I know, currently. The decrease in band is interesting to note. The decrease over the years was not due to learning more rules, but it was due to more and more of the printing press crews adopting the rules. They saw their colleagues adopting these rules and removing time delays as well as increasing the quality of product. And so as these things were adopted in the plant, the problem decreased. So to some extent, that's the end of the story. Featural representations are good. They can be used to describe state, in this case of printing presses running through time. And machine learning, which we haven't detailed as yet, was instrumental in solving this. I just want to touch on some possible relationships between machine learning and constraint satisfaction, which is the topic that this video is to some extent motivating. Or the constraint satisfaction problem is given below. You're given a set of variables, a domain for each variable. And you've certainly seen that in the data description. We have over 30 variables, and we're told in the previous chart what the possible domains are. Chrome solution ratio, for example, which is the CSR column in this table above, has a range of 0 to 200. Then there's a set of constraints, and the constraints in this case, you can look below. The machine learning system is given a constraint, banded equals no. What you want to find in a constraint satisfaction problem is an assignment of the variables to particular values that satisfy the constraints. Given the constraint satisfaction is defined here, the solution is trivial. You can take a look at each assignment found in a not banded snapshot, and that would be a legitimate assignment of values that would correspond to the constraint that we wanted to enforce. But really what's going on in machine learning is somewhat more general. We want to discover, if you will, a set of states in which banding doesn't occur. And we can identify that subset of states by finding the subdomains of variables that correspond to the non-banding data or snapshots that we found. So the machine learning system is in some sense taking a very simple constraint, banded equals no, and is coming up with other constraints. What has to exist about the data so as to avoid the band? And in green, I'm simply reminding you of one complex constraint that was discovered through machine learning. You'll notice that none of these constraints, chrome solution ratio greater than T1, ink temperature less than or equal to T2, none of these constraints represents relationships between variables per se. A constraint that would represent, say, a relationship between variables might be something like the ink viscosity in printing unit 1 must be roughly the same as ink viscosity in printing unit 2. That could be an example of a relationship between variables that would represent a more complex constraint, and frankly a kind of constraint that makes constraint satisfaction problems more interesting. So just to summarize, again, simple relationship between machine learning and constraint satisfaction. We've got an environment that includes variables, snapshots or state descriptions, and constraints. In this case, a high-level constraint that banded should equal no. The machine learning system is taking this environmental input and it's learning constraints on features. The set of states in which chrome solution ratio is greater than T1 and ink temperature is less than T2 and ink viscosity is above T3. This represents a set of states implicitly. Even in this case, where the machine learning system didn't discover certain constraints like relationships between attributes, I show here in red that the human crew is a learning agent as well, and they have their own rules that they have learned through experience, like the importance of, say, uniformity between ink temperature across different printing units, and they're using those to control printing operations as well. Again, don't want to make too much of this relationship between machine learning and constraint satisfaction just yet, but I think it's interesting, and it brings out this relationship that Poole and Mackworth are trying to make between featural representations and state-based representations. Finally, if you want to follow up on any of this work on machine learning and rotogravure printing, you can have a look at a couple of papers. At least the first one, there's a preprint that's online, and the other one may be online as well. Just do a Google search.